To start with, gas stoichiometry uses the ideal gas law to solve stoichiometry problems for chemical reactions involving gases at any temperature and pressure. Before using the ideal gas law, it is necessary to write and balance the chemical equation for the reaction. So for the first example, say you were given a word problem in which you were able to derive the chemical equation of propane and oxygen gas combusting to form carbon dioxide and water. And you were given 7.8 liters of oxygen gas with excess propane. You were then asked to find what volume of carbon dioxide can you form with 7.8 liters of oxygen gas while it reacts with excess propane. So to be able to get the answer, you will need to use the coefficients of the elements in the chemical reaction as the ratios of the volume of the respective gases. So let's try to solve the equation. You multiply 7.8 liters of oxygen gas by the ratio of oxygen and carbon dioxide in the chemical reaction. So 5 liters of oxygen gas would make 3 liters of carbon dioxide. You can then cancel the units. So with an equation of 7.8 times 3 over 5, you have the answer 4.68 liters, or following the number of significant figures, 4.7 liters of carbon dioxide. So for this next example, you have the given balanced equation of acetylene plus oxygen gas combusting to form carbon dioxide and water. And this will be an example of a volume to mass equation, wherein you are given 2.64 liters of acetylene. You are asked to find how much oxygen in grams is needed for the reaction to take place. Again, we are going to use the ratios of the coefficients of the elements involved in the reaction. So to solve this problem, you multiply 2.64 liters of acetylene with the ratio of oxygen and acetylene in the balance equation, wherein you have 2 liters of acetylene and 5 liters of oxygen for the reaction to take place. And you can cancel the units, giving you the answer 6.6 liters of oxygen. So using the ideal gas equation of PV equals nRT, we have 1 atm at standard temperature and pressure multiplied to our value of 6.6 liters of oxygen gas equals to the number of moles, which will be mass over molar mass, since we're looking for mass, and our molar mass is 32 grams per mole, multiplied to our gas constant of 0.08206 atmosphere liter per mole Kelvin, and our temperature of 273.15 Kelvin. So simplifying the equation, we have 6.6 liter atmosphere equals m over 32 grams per mole multiplied to 22.4146 atmosphere liter per mole, since we're able to cancel Kelvin. Now you can divide both sides by 22.4146. And canceling the units, you can get the answer 0.294 moles equals to m over 32 grams per mole. So you multiply both sides by 32 grams per mole and cancel, which gives you the final answer of mass equals to 9.42 grams of oxygen gas. Or we can use another method of converting liters to grams, which involves using the conversion factor of 1 mole is equals to 22.414 liters as per standard temperature and pressure. So in this case, we have 6.6 liters of oxygen gas, and we multiply that to 1 mole of oxygen gas over 22.414 liters of oxygen gas, and cancel the units. And now we convert moles to grams through the molar mass, which is 1 mole of oxygen gas has 32 grams of oxygen gas, which would give us the answer 9.42 grams of oxygen. With our next example, we have this word problem How many liters of carbon dioxide is formed in a combustion reaction with 1.25 liters of methane and 2.35 liters of oxygen gas? So first, we have to identify the chemical reaction and the equation for that chemical reaction. So in this case, our balanced equation is CH4 plus 2O2 resulting in CO2 plus 2H2O. And since we have two values of volume, which is methane and oxygen gas, we first have to find out which one is the limiting reactant so that we may solve for how many liters of carbon dioxide. So just like in reaction stoichiometry, to get the limiting reactants, we have to divide the values of the volumes with the coefficients of our chemicals in our chemical reaction. So first, for CH4 methane, we have 1.25 liters divided by 1, which is its coefficient, which would give us the value 1.25. Next, for oxygen gas, we have 2.35 liters, and according to the equation, we need 2 liters of oxygen. So divided by 2, we have 1.175. And for limiting reactant, our chemical with the lower number is our limiting reactant. So in this case, that chemical would be oxygen. So now we can use 2.35 liters to find out how many liters of carbon dioxide is formed. So first, we multiply 2.35 by our ratio of coefficients, which is 2 liters of oxygen gas yields 1 liter of carbon dioxide. So canceling the units, we have the answer of 1.18 liters of carbon dioxide.
In this next example, we have the problem 4.45 grams of magnesium carbonate is heated until it decomposes into carbon dioxide and magnesium oxide. What volume of carbon dioxide gas will be produced at STP? So again, the first thing we will need is the balanced equation for this reaction, which in this case would be 1 magnesium carbonate decomposing into carbon dioxide and magnesium oxide. So in this problem, we are asked for the volume of carbon dioxide gas with a given of 4.45 grams of magnesium carbonate. So in order to solve that, we first convert the grams of magnesium carbonate into its mole using the molar mass. So the molar mass of magnesium carbonate is 84.32, as it is 24.31 plus 12.01 plus 16 times 3. So that's 84.32 grams. Which per 1 mole magnesium carbonate. Cancel that. And now that it is in mole form, we can now convert magnesium carbonate into its carbon dioxide using the mole ratio. So that is 1 mole magnesium carbonate. And according to our balanced equation, 1 mole of magnesium carbonate converts into 1 mole of carbon dioxide. 1 mole of carbon dioxide. Again, you can cancel the units. And since it is asking for the volume, you can use the conversion factor of 1 mole of a gas is equal to 22.414 liters according to the standard temperature and pressure of ideal gas law. So 1 mole carbon dioxide equivalent to 22.414 liters of carbon dioxide. Again, canceling the units, and 4.45 grams divided by 84.32 multiplied to 22.414 liters will give you the final answer of 0.18 liters of carbon dioxide as the volume produced by this reaction at standard temperature and pressure. For our next example, we have magnesium nitride reacts with excess water to form ammonia and magnesium hydroxide. If 4.7 liters of ammonia gas was collected at 300 Kelvin at a pressure of 1.6 atmospheres, how many grams of magnesium nitride was consumed? Since we don't have this equation at standard temperature and pressure, we're going to have to convert it into moles using the ideal gas. So the equation CV equals nRT. You have your pressure of 1.6 atmospheres and your volume 4.7 liters of ammonia gas equal to the number of moles, your gas constant 0.08206 atmosphere liter over mole Kelvin, and your temperature of 300 Kelvin. So we can cancel these units, and you have 7.52 atmosphere liter equal to 24.618 atmosphere liters per mole. And you divide both sides by your, your atmosphere liter over mole to isolate your N, divided by 24.618. And cancel that, and cancel these units, and you have N, which is equal to 0.306 mole of ammonia gas, and H3. Now that you have it in moles, we can once again use our balanced equation to convert our moles of ammonia gas into how many grams of magnesium nitride were formed in the equation. Okay, so now that we have the number of moles for ammonia gas, we can now use our gas stoichiometry to find the amount of magnesium nitride consumed in the reaction. So first we have the balanced equation of magnesium nitride, water combining to form ammonia gas and magnesium hydroxide. So using our balanced equation, we have 0.306 moles of ammonia gas and our conversion factor of 2 moles of ammonia with 1 mole of magnesium nitride. You can cancel those units. And since we are looking for grams, we have to convert the moles of magnesium nitride into grams using its molar mass. And magnesium nitride has a molar mass of 100.95. So that 1 mole of magnesium nitride every 100.95 grams. Once again, you can cancel the unit. And the final answer to this equation of 0.306 times 1 half times 100.95 is 15.45 grams of magnesium nitride. Or taking the significant figures into account, we have the lowest significant figure of 2. That would be 15 grams of magnesium nitride.